Today we'll be speaking in collaboration and presenting the efforts of the Dark Matter Science Project running on the VRE platform. So we're gonna try to keep it quite short, probably within the hour. And we're gonna start with a very general introduction of the purpose of the project and in general of European projects tackling running physics workflows on large infrastructures. Then we're going to introduce in more generally how a common infrastructure could serve the needs of dark matter searches. Then I'm gonna delve a bit deeper into the infrastructure components and how the data management is done and the workflow distribution is done on the platform that we call the virtual research environment. And then Jared is going to delve a bit deeper into all the science projects that compose the Dark Matter Science projects. And if we have time at the end, we prepared a very little video demo showing how EOSC resources are integrated into the platform. And we're going to end with some conclusions. So just to give a very general introduction, we see that the LHC at CERN was the first big, large scientific experiment to generate petabytes of data per year. And you can see this in the plot on the left, where there is a plot of the data volume growing exponentially year by year. And you see if you apply conservative R&D projects or aggressive R&D strategies, but you can anyways see how the data volumes are really growing exponentially. And so at CERN, the technologies to manage and process these large amounts of data were initially developed many years ago. But right now, as you can see on the plot on the right, it's not only high energy physics that is producing these terabyte scale data, but it's also there are also other sciences such as astronomy, and you see an SKA plot on the right where you can see that the data is also growing in a very, very fast fashion. So there are next generations of detectors, antennas, and telescopes that are trying to adopt the same solution. And with these projects, we're trying to find a common infrastructure across research facilities and across research centers and across institutions within European projects that would allow, of course, an economy of scale, the collaboration between different physics domains in the name of scientific reuse and sustainability in the long-term plan. Because, of course, if we manage to build infrastructures to manage and process data and conduct analysis in a cohesive way between physics sciences, we're going to eventually try to find ways to economize the efforts and also be more sustainable in the future in order to avoid doing the same thing twice or three times or multiple times eventually. So in general, in the context of reproducibility, there is this very interesting Nature research paper that says that 70% of researchers, not only in physics domains, but also in chemistry, biology, and all the other ones that you can see on the left of the plot, have failed to reproduce other people's research. And this is a huge amount. This is a very, very big number. And in the future, all the scientific efforts in many domains are targeting basically they're trying to bring this number down. And also more than 50% of researchers actually fail to produce their own results. So as we said, in the name of sustainability of results and data, we are really trying to bring researchers together, try to use the same tools and try to use the same procedures and technologies to make the results more reproducible and eventually more shareable. So in this context, EU collaboration, European efforts are funding and promoting projects to promote cross-fertilization across research infrastructures and scientific domain to find common, consistent, and useful solutions to solve the challenges of transfer services, data management services, distributed data processing, sustainability of software and versioning of software, and the construction and the development of analysis facilities that allow preservation and reusability of analysis. More in the specifics, there is the ESCAPE project, which is an EU-funded project that aims to bring together different research infrastructures. It's composed of 10 research infrastructures, 2 pan-European international organizations, and 4 supporting European consortia. And you can see on the right what all of the work packages of ESCAPE have worked towards. The ESCAPE services will contribute to the European Open Science Cloud through the EOSC Future project, which is the one that we are mainly funded by and we are mainly working within. So basically 2 main science projects, the dark matter and the extreme universe science projects. Today we're going to be talking about the dark matter science project, have been developed to demonstrate, to bring together all the services that have been implemented within ESCAPE. And you can see on the right on this graph, there is the software repository, the analysis platform, the data management for open science, the citizen science, and the virtual observatory. So all of these come together in the EOSC project, and the science projects are a practical way to gain new insights and innovation across disciplines, to improve the productivity of researchers, and eventually demonstrate an open science approach to dark matter searches. And the virtual research environment is an open source analysis platform that is developed at CERN. Is a platform where researchers have access to all the digital content to develop, share, and reproduce an end-to-end scientific result. So to the data, to the software, to the environment, and to everything that comes to reproduce the result in compliance with FAIR principles. FAIR stands for findable, accessible, interoperable, and reproducible. So you can see how we have different European science clusters that you can see on this. I also have the pointer. So here are the science clusters, and here are the research infrastructures that basically feed into the EOSC Future project, which is part of the European Science Cloud, which is a huge project. And with the virtual research environment, we're really trying to bring together researchers. So, of course, the efforts need to come from people who do the science and who give us the feedback of how to implement the platform, where we host the community software, but we also try to make it very easy for IT administrators in other institutes to redeploy this whole infrastructure that I will describe the components in a bit. So this is a bit the timeline of the project. You can see that the first data lake, so data management prototype in ESCAPE started in 2019. The ESCAPE project formally finished, but an open collaboration agreement has been signed to keep going in the future. And the EOSC Future project was put in place to demonstrate the capabilities, as I said, of the ESCAPE tools. And the initial design of the virtual research environment started in 2021. The science projects have been onboarding the virtual research environment in the development phase to, as I said, work really hand in hand between IT administrators and scientists. And the projects have been presented in plenary talks just last month at the Computing High Energy Physics conference in Norfolk in the US in 2023, and have had quite a lot of success. So right now I will leave the word to Jared, and he's going to introduce a bit the dark matter, how this general platform and common solutions can benefit physics researchers of dark matter.
Thank you. Yes, so dark matter is one of the biggest scientific questions today. We have a lot of evidence for dark matter, but it is primarily astrophysical evidence. So we really need to understand what this 85% of invisible matter is. However, dark matter experiments, they are very large, complex, and costly experiments with only one or a few of each type in the world. So it is really imperative to maximize each experiment's scientific outputs. This includes creating new analyses, but also storing these analyses, data sets, and results. to allow us to combine multiple results from different experiments and reinterpret the existing studies to answer future questions. So for context, the EOSC Future science projects are demonstrating a multi-domain science integration across the EScape services and unifying under one proof of concept analysis platform. Is also demonstrating the interdisciplinary open science from a bottom-up effort. So you see we have a general idea here on the right of the VRE where we come in and so a user can authenticate to gain authorization, and we bring together in the computing platform both their data, but also their analysis objects, so their code and analysis environment as well. So the dark matter science project, we're focusing on weakly interacting massive particles. These particles interact with ordinary matter or standard model particles. And we have, sorry, you do not use that. We have, yeah, I won't use. So on the left, you have an example of these interactions where you have the two dark matter particles on the left and standard model particles on the right. And the different experiment types can be summarized by going different directions. So for an indirect detection process, you'll have two dark matter particles come in and interact and annihilate into two standard model particles. So we call this breaking dark matter. But you can also shake dark matter in the direct detection experiments where you have a dark matter particle come in and interact directly with a standard model particle, and you can observe this interaction. Whereas at collider searches, we're actually going the other way, where we have standard model particles colliding at high energies in order to try to produce dark matter particles. But a joint discovery of this nature will require, the different experiments to be able to work cohesively. But these different experiments have different data sizes, workflows, and result sharing policies. So just to give an example of a potential discovery scenario, just presume that a direct detection experiment can see a hint of a signal with this WIMP dark matter characteristics. And some years later, another direct detection experiment that uses a different technique may confirm these hints. And then we have an indirect detection experiment that observes some dark matter annihilation that is compatible with these signals. So we might want to target particles at a future collider with the mass of this dark matter candidate in order to shed some light on the interactions between the dark matter and the ordinary matter. But such a scenario will require us to be able to work together, to interoperate and reproduce each other's analyses in order to be able to compare and combine the different results from these different experiments, as well as provide end-to-end workflows so that we can make the analyses available for cross-checks. So we're trying to build a prototype here that fulfills these requirements. Just to give you some idea, the experiments that are involved in the dark matter science project, we have some of each type. For direct detection, we have dark side at colliders, we have the Atlas experiment at the LHC. And in the indirect detection experiments, we have Fermilab and KM3Net, as well as the evolutions of these experiments going forward. So with this, we're trying to understand the computing analysis challenges for some of these future experiments, dark matter experiments. Just some scientific outputs for the dark matter science projects that we have. We have worked towards individual results and publication. So publishing new scientific results in the different experiments. And trying to produce the plots that highlight more the complementarity of these different experimental efforts. All of the data and software objects and pipelines are stored with the data on the data lake, software on the software catalog, with the pipelines made accessible in the VRE. So going forward, we won't have time in this project, but it facilitates this combination of these different results. So you can see a couple of examples of some combination plots in the top right. So for example, in the first plot, you have a direct detection experiment with the green line, different experiments being able to facilitate this combination with the collider search in red. in order to further understand the exclusion of dark matter in the space. So the different experiments, they have different workflows, as I mentioned before, but we have a sort of common workflow in the Dark Matter Science project across these experiments. So every experiment may have they come with their data, and they may have generation and simulation data as well. And they will need to process this data before passing it to the analysis stage to be able to analyze the different events and distributions and distinguish between the signal and the background processes, and then they interpret their results. And if we can create this on the virtual research environment, it will be much easier to facilitate this combination of these different results. Then I will pass back to Elena to discuss more of this virtual research environment.
Yeah, we thought it would be easy to first introduce kind of this infrastructure that he's talking about. So this virtual research environment is really what brings together both the data management in the beginning and then the analysis distribution in the end. And it's used by all of the dark matter researchers to find a common solution to run their workflows. And then Jared will come back to talk a bit more about the science. So I will try to make it quite understandable by everyone. The building blocks of the VRE are mainly divided in 4 parts, which are first and foremost the authentication and authorization of all users through a common layer, a federated authentication layer. Then, of course, as Jared said, the first part would be the data management procedure, where the data is really produced at the experiment site and is injected in what we call the data lake, which is just distributed storage across Europe, managed by different partner institutions. Then the researchers are able to use a notebook service, which is gaining more and more popularity, such as Jupyter notebooks, to run their analysis. And once the analysis once the preliminary analysis is done on Jupyter notebook services, the analysis part, so the computing part, is integrated into the analysis by dispatching it to cloud or HPC resources. And all of this, the main core of the infrastructure, is managed by Kubernetes and it's hosted on OpenStack virtual machines hosted at CERN. And the whole thing is managed with GitHub repositories, following the guidelines of continuous integration and continuous delivery and container orchestration and infrastructure as code techniques. So we'll really fly through the 4 main components. So the authentication and authorization is managed by the Indigo Identity and Access Management platform, which has been recently adopted at CERN as well for WLCG, the World LHC Computing Grid, because it supports very well token authentication. High energy physics has been authenticating users through X509 certificates, which where users have to request a certificate and then they have to be added as part of a virtual organization. This sometimes is a bit cumbersome, as at CERN it's very easy because it's a high energy physics common technique, but other sciences do not have access to X509 certificates very easily. So what we're transitioning towards is OIDC tokens. So the token logic is really definitely gaining ground. And our authentication and authorization infrastructure is the same used by the ESCAPE community, and it's managed in Bologna, in Italy, by INFN on a Kubernetes infrastructure. And then once a user obtains an account on that infrastructure, there is a cron job managed in Kubernetes that basically updates our databases to allow users to use all of the underlying services, meaning the data management, the software, and the computing resources. So one of the more interesting parts after authentication and authorization is the data management of all the experiments. So there is our core infrastructure is hosted on Kubernetes, but it is connected to a data lake of experiment data that is spread across Europe. And the data management is done with Rusio. I put a link there. I think all of you are familiar with it, but some might not. So Rusio is really an open source and data management and orchestration project, which was initially developed by the Atlas experiment at CERN to manage petabyte of data per year. And it is now, though, used by CERN and non-CERN communities to manage, again, as I said in the introduction, really, really large amounts of data. And the data lake is just a distributed data infrastructure, which is policy-driven and reliable, and is able to deliver data at low latency to all types of processing facilities. And the storage elements are managed, as I said, by partner institutions and are spread across Europe, as you can see in the plot on the left. So the Rusio main and authorization servers on the cloud infrastructure manage all of the user authentication and the user upload and download of the data. They're connected to a central relational database hosted at CERN, with connected to backup services in case of major failures. And then the database and the Rusio servers are connected to daemons which are basically in charge of all the processes for data upload, download, and transfer between all of these facilities and storage elements distributed across Europe. And the storage elements support different storage technologies, such as EOS, DPM, Dcache, Storm, XrootD, and S3 lately, so also the cloud protocols. And the data, as we said, are uploaded and downloaded to the data lake through data access libraries developed initially at CERN, such as GFAL. And then the transfer between different storage elements is done with FTS, which is also a file transfer service, initially a project developed at CERN that supports many different kinds of protocols, such as grid FTP, HTTP, and HTTPS, WebDAM, Xroot, and Xroot protocols. So this is a bit the what we call the Rusio instance of the project. Then once the data is uploaded and downloaded on the data lake, to facilitate interactive analysis, what we have is just a notebook service, a Jupyter Hub interface, where, as you can see on the right, the user is able to select different environments hosted in containerized repositories that we are hosting on Docker or on GitLab and GitHub. The notebook service is connected to the CERN virtual machine file system, which is installed on the terminal, so it's accessible by different experiments by the terminal. And the different client libraries, such as the Rihanna client, the Rusio client, are already installed in the terminal, so that the scientist's analysis is facilitated by not having to run installations of different packages to interact with the underlying services that are mainly hosted on CephFS volumes, which are mounted on the main node of the Jupyter Hub. Within the ESCAPE project, a Rusio extension has been integrated in the notebook service. So as you can see, I put a screenshot there. There is a possibility to browse through the data lake that I just described before by just very interactively and an easy way clicking on the extension. And each researcher is able to browse through the other experiments' data. So to browse through the data that other people have uploaded. And then they are able to very easily choose a file, assign a parameter to it, and then run an analysis, import it into the notebook. That would be on the right of this screenshot. And a user is able to interact with their own data and with other people's data in a very easy and intuitive way. So what happens behind the scenes is really, let's say, for example, Jared wants to run his analysis on the Jupyter Notebook. The Jupyter Notebook is hosted at CERN, as you can see here in Geneva. But let's say he wants to use the data that somebody else has uploaded at INFN in Italy. So what he does is he requests the data to be brought next to his notebook. And there is a storage which is fuse mounted on the node, and the data with the daemon processes that I described before gets replicated into the storage that he next to his notebook, where he has the processing power, and then he's able to process the data there. So now this is a bit more in the notebook fashion, but some people really also like to dispatch the workflows through the workflow languages. So when larger and more complex workflows come into place, we also need to deploy and develop solutions to distribute the analysis and preserve the analysis for reuse. So the main resource managers are Kubernetes, HTConder, and Slurm. And the main workflow schedulers are Dask, Rihanna, Spark, and other ones. So what we have is, again, the main infrastructure is hosted on cloud resources, but then it's the connection to machines connected over any network. So it can be a cluster of cloud resources or local and grid resources need to be connected to the notebook. So basically the user sees the notebook and then is able to dispatch and create Dask clusters or connect to remote clusters through the terminal. So we have been largely using Rihanna. Rihanna is a reproducible analysis project developed at CERN to make the preservation of analysis very easy. So it supports the intuitive declarative programming approach. So it has this kind of like more workflow approach logic, where a user comes with a Rihanna.yaml file, which contains a reference to the input data, a reference to the software environment that he wants to use, a reference to the code, and the computational steps that he or she wants to run. And then Rihanna is connected to a database and is connected to a job controller that connects to either cloud resources or remote resources. So this would be a cloud resource cluster, and this would be just the connection to remote larger compute resources. So the data is brought next to the shared storage, which is close to the nodes of the processing nodes. And then Rihanna supports different workflow engines to distribute this workflow to all the nodes of the infrastructure. And lately we have developed an authentication through Russia, where the data really gets brought next to the shared storage. So the analysis becomes completely independent of the local storage of the user, because to give again an example, let's say Jared puts his data in CERN or something, and then somebody else wants to run an analysis with this on distributed nodes with Rihanna. The first step of the analysis would just be like calling who's your client, getting authenticated in this common federated way, bring the data close to the Rihanna shared storage, and run the workflow on remote data, basically. Lately, we've also been deploying this Dask interface on the Jupyter Hub, which is another way, basically, of distributing the workflow in a Pythonic way, and it has all these nice dashboards to see the work in progress, and it has, again, it's integration between Jupyter Hub and Dask. I will finish by saying that we also have infrastructures in place to aid researchers to see if their upload and download of data and transfer of data has been successful on the data lake. So we have monitoring and testing in place of all the different storage elements that are hosted on Grafana dashboards at CERN. You can see here a visualization of it. We also have user interfaces, so graphic UI interfaces. This would be the Rusio interface. I will also have a little demo about it, but you can see all of your data, where it has been uploaded. RSE stands for Rusio storage element, where it has been uploaded, and if the replication has been successful or unsuccessful. And on the left, you can see the Rihanna UI, which has been just applied by Helm charts to the infrastructures. And again, you can see all the steps of your analysis, and you can see if the analysis has been successful or not. And we have a very nice, we hope, user documentation that is being really updated daily by following the advice of all the dark matter researchers. That is hosted on GitHub pages, and we also host all of our deployment on GitHub repositories that are completely public. And although they are deployed on CERN infrastructures, so they are somehow sometimes CERN specific, we're really trying to make all the softwares of Rihanna and Ruscio, which are initially developed at CERN, more accessible to different research infrastructures and different institutes which might not have the expertise of deploying such a quite a complex infrastructures. So we're really trying to make it as accessible as possible to all the experiments. And we also host forums and discussions between researchers to facilitate collaboration. So this is a bit an overview of our platform. And now Jared is going to talk again how it is used in all the science projects.
Thank you. Yes, I'm going to go through a few of the different experiments and discuss how we utilize all of these tools. So first I will start with dark matter at particle colliders, namely searches in the ATLAS experiment that I am working on. So as I'm sure you know, the ATLAS experiment, along with CMS, is a general purpose detector located at the Large Hadron Collider that studies a wide range of physics questions, including searches for new physics. So these might be particles that make up dark matter. So importantly, at the LHC, we're trying to make dark matter by probing these interactions so we can understand better the nature of dark matter. As you see on the right, these interactions may include new particles that we may see and better understand this interaction. So first, I want to talk just briefly about a previous analysis, because two projects I'm working on within this science project both kind of continue on this previous work. So you can see in the left is the previous dilepton inclusive resonance search. The plot here summarizes the results from this analysis. And you can see that for the red line, the solid red line, it's a fit to the expected standard model backgrounds. And then the black dots are the data that we observe. Whereas with the red dashed line, it's as if this is what we would expect to see for some different signal samples, some different parameters. If we saw the standard model plus this new particle that this resonance can create. So in this case, it's just the dielectron results. We also performed this for the dineon, but you see that there was no signal here. So the analysis moved to constrain, set limits on these fiducial cross sections of this Z prime particle. So the two projects that we're trying to include on the VRE is a reinterpretation of this resonance search in terms of dark matter mediators. And as well, we're developing a new exclusive analysis looking for Z prime plus some MET in order to target these high backgrounds in the lower mass region, further to the left in the plot. So for the reinterpretation, if we assume that there's a non-zero coupling to leptons for some neutral mediator that may couple with the dark sector, we would expect it to also produce an excess in this mass distribution I previously showed you. So we can take these expected limits that we set and produce new samples and find where we can set the limit on this fiducial cross section. So it's a two-step process that you have to generate one sample that's for different masses for potential dark matter masses and set the limit, and you can then find this limit and create a summary plot and scan over many different masses as shown in the center plot here. On this, I just want to say, I show you the plots that we produced on the VRE, and these results were included in the US SNOMAS effort, which aims to benchmark what we expect to see. So we extrapolated these limits for high Lumi LHC conditions in order to gain an outlook on the expected limits of the high Lumi LHC. So these results were summarized in the purple on the plot at the right in combination with the other analyses as well. So here I just wanted to demonstrate that we also set this up to run using Rihanna, as Elena described. It's a really nice platform for utilizing distributed computing resources. So set up my YAML file and was able to, from the VRE, send this job to a remote cluster and run this two-step process, which is one of the nice features of Rihanna, that you can define different workflow steps, because as you expand into a full end-to-end workflow, you need to be able to pass different steps of the analysis, and this may include very large data. So it's nice that you can do this all remotely and in a pretty seamless way. So this was used to first test this feature. But for the Z prime plus meta-analysis, we have, as I mentioned, some well-motivated models that could have escaped detection in this large background region. So by targeting dilepton events with MET in the final state as well, we'll be more sensitive in these regions. So this is an analysis that is still in progress. We expect very soon some results, but they're not public yet. But I wanted to just say that we are using this analysis to try to further stretch this feature and start earlier in the workflow from larger data containers in order to troubleshoot any potential issues we may see. So far, we started from what we call a DAOD, which is a very large containerized data set. So just to give you an example, some of our background processes at this stage are for one background process, we see samples greater than 10 terabytes. So this is another nice feature about Rihanna working with Rusio, is we can use, in this case, I use the official Atlas recast platform using workflow language to set up the first two stages of our in-progress analyses. And this is really nice because for these really large data sets, it splits up the different files. So for one large data container, there's many files that are much smaller, and it's parallel. You can run it in parallel much more easily in this way. So for now, I'll talk about the direct detection plans and results from DarkSide. So DarkSide is a liquid argon TPC that's looking for elastic scattering and measuring both the scintillation and ionization of these events. They recently concluded the DarkSide 50 in 2018. So here, this is what I'll show you are results from this experiment, but they're currently transitioning to DarkSide 20K, which will begin in 2026, and it's more than 10 times the volume of DarkSide 50. So for them, they implemented a reanalysis tool for high mass search, all on the VRE platform, including some output plots I show you here on the left. They have a DarkSide 50 exclusion curve for a high mass analysis. So you can see on the left, they have a Jupyter notebook that they connected the data and were able to produce these exclusion curves. Further work is still ongoing. They aim to add a low mass analysis as well to implement a low mass analysis. And you can insert different theoretical models to produce different limit results. And here they're working towards the first open implementation of this. On the indirect dark matter searches with gamma rays, this is being worked on by Pooja and Christopher. So in this case, for indirect searches, you can have gamma rays or neutrinos. So here we're looking at gamma rays, and there's mainly two ways to target gamma ray searches. For high energy, you have the land-based telescope arrays. But here we're focusing on low energy gamma rays looked at by Fermilab Space Telescope. So here they implemented the machine learning Fermi dwarfs, which is an algorithm to predict the gamma ray background over the entire sky by training on gamma ray measurements, real data measurements from Fermilab, using a machine learning approach. So this is a previous work I reference here from Francesca Calore and Alvarez previously. So the data and the main processing software for this are all publicly accessible, and now they're fully available in the VRE. And the code is entirely written in Python 3 with well-known packages, for example, scikit-learn. And this package can be optimized from the command line to allow a quick check of the viability for user-defined dark matter models. So here we have some results from the VRE. You see the same exclusion curves from the paper were reproduced on the VRE, much in a similar manner with the data on the data lake, and the code is publicly accessible here. As well, they have the more recent brown dwarf analysis from Pooja. It was a recent publication where they set new limits shown here on the left two plots. And I think a big takeaway here is that on the right, you see that their limits are getting closer to dark side as well. So this is a good potential collaboration area. Now I'll discuss just a bit the instrument response function for KM3-NET that Mikhail is working on. So KM3-NET is a cubic kilometer neutrino telescope located at the bottom of the Mediterranean. It consists of two parts, ARCA, which is looking at high energy cosmic neutrino sources. This is located off of Sicily at a depth of about 350 meters. 3,500 meters, and as well as ORCA, which is determining the neutrino mass hierarchy, looking at low energy neutrinos, which is based offshore of Toulon in France. So the concept of the instrument response function is it provides a quantitative estimate of the different event and background rates. So it contains all of the characteristics of the detector, and it allows them to avoid Monte Carlo simulations each time with different neutrino source configurations. It supports different configurations of neutrino sources and is compatible with gamma pi, which gives an easy combination with other gamma experiments like CTA. And this package is actively developed. It's an actively developed Python package. You see it's easily available. So there's also common tools that we want to include on the VRE for everybody to use. So in this case, machine learning for compressing big data. Baylor is a compression tool that trains on the autoencoder of scientific data. It compresses and decompresses it by storing the model as well as the autoencoder's latent space. Allowing the storage of fewer dimensions. And yeah, so we wanted to provide this as a sort of off-the-shelf algorithm that anybody would be able to use. So currently the Jupyter notebook for this prototype is available on the VRE, but there were many recent improvements. So these will also be ported on the VRE as well. Oh, yeah, okay, so at the demo, maybe you want to...
Thank you. So I think we are almost done. We wanted to show a little video of what a full workflow would look like, basically uploading data on the data lake, performing an analysis on the notebook, dispatching the notebook, the workflow to large computing resources, and in the end, just outputting a plot. So I have a little video of what Jared discussed in his atlas analysis. This is actually his thing, so I can talk over it, but I can also, it's also a bit on the integration of EOSC resources. So we've been provided with by CNAF and Prague to have both on one side the storage and on one side the computing resources. So this video just briefly, wow, it's very fast. So, okay, it shows a bit all the components that we discussed. So first and foremost, a nice website that we have where a user or like a citizen or any kind of person can browse through and can read the dark matter, for example, dilepton search. Then the user can see the software in the software repository on GitLab. And then he or she can browse through the notebook service. From the terminal, he or she can authenticate to Lucio. can use the Jupyter Lab extension by being already authenticated with OIDC token and can browse through the data. So the data has been previously by Rusio commands uploaded on this SESNet S3, which is a 1 terabyte cloud storage provided by EOSC Future. And then the user can run a Rusio upload command with all of his data that is present, for example, locally. Then through the Rusio UI, you can see that, for example, by filtering through, you can see your data is there on the SESNet RSC. And from here, we can see that there is a notebook looking at this data and trying to produce a plot. So you can run a preliminary analysis with, for example, a few steps on the VRE, on the notebook service, and then you prepare this YAML file. Maybe I can stop a second. So you prepare this YAML file with all of the steps of the analysis as Jared described. So the first step would be fetching the data from the Rusio RSC. And the second one we test by doing a Rusio UMI. And the second one would be performing this analysis that sets the dark matter limits and runs on the Kubernetes backend. And then the plots are the output. So this is the run Rihanna bash file. The Rihanna client is already installed as a library on the notebook. And then through the Rihanna UI interface, which is provided by, again, here you can see that we have set up an IP address so Rihanna has been installed on this cloud, on the OpenStack cloud infrastructure at CNAF in Bologna, because again, this has been provided by EOSC Future. So, and we can authenticate through here via the common EOSC authentication layer. And so the user is able to dispatch it to all of these resources. You see, those are the nodes of the infrastructure. And he or she is able to dispatch the workflow. And here I show the user authentication, the user documentation for an easy onboard while the workflow is running. It's running. It's taking actually not that long. And from here, you can see that the first step is fetching the data from Rusio, which has been successful. So the data is brought close to the Rihanna storage. And the second thing also runs well, and the plot is outputted. A further step could also be having, again, a Rusio step, uploading this kind of data on the VRE. And this is a nice proof of concept of the workflow running on VRE resources. So now I will just go through the conclusions. So overall, the dark matter science projects analysis are running on the virtual research environments, and the new scientific results are being produced on it. Multiple communities with the necessary understanding to reproduce the analysis are taking part in the project. And as Jared showed, there are possibilities of already comparing and combining, for example, the Fermi-Lat and the dark side analysis, but we're still working and, of course, fostering collaboration and communication between researchers and between different experiments. But this is a proof of concept that a common platform is there in place to tackle the challenges of fair data and interoperable workflows within and across different physics communities. So the VRE is a working prototype for the EOSC Future, for the European Open Science Cloud. And it is a good testing ground for software and computing that can be explored for future experiments, and not only actually in the physics domain eventually. As I said before, the ESCAPE Open Collaboration Agreement has been, and there is a link to it, everything that is underlined is a link, ensures the collaboration and joint common activities across communities. So it's definitely an example and a proof of how the project has been successful in developing and testing new solutions for different sciences. EOSC resources, as has been shown in the demo, have been integrated in the platform, and it is also quite good that our work has awakened interest from various scientific domains, which are not only high energy physics, which are still in the early stage prototypes phase. So, for example, they are building telescopes. SKAO has been being built, or they are building computing centers to process large amounts of data. We have been contacted to give presentations, for example, by the Einstein telescope, people that are exploring ways to manage their large data once the experiment will be in place, by the Nucleus experiment, which investigates elastic neutrinos capturing, and by the German Center for Data-Intensive Radio Astronomy, which is currently also being built as a collaboration. And also there is interest in our project by different other European projects which explore new digital models to reproduce science, for example, digital twins. So overall, it has been a very successful journey, we would say. There are definitely future plans that can be investigated. First and foremost, the consolidation of EOSC Future science projects. So as Jared showed, there is already many projects being onboarded, but it would be nice to widen the participation of scientists to open science tools by onboard new analysis requiring order terabytes of data management. And we have to still deal with the embargoes put on data that are restricted by the whole collaborations. So this has been a bit of a challenge because, of course, some collaborations and experiments don't allow data to be shared, and our solution is an open source solution. So it technically allows users to browse through other users' data. So this has been definitely a bit of a limiting factor, even if we are trying to push for open data and collaborative software and collaborative data as well. We are in the phase, as Jared showed, mainly in his analysis of Atlas, to expand the use cases to real-time analysis and more complex workflows on constrained infrastructure, because in the end, it is a proof of concept. Our infrastructure is not really a production grade infrastructure. We also want to ensure, as the project is coming to an end this summer, we want to ensure the sustainability of the infrastructure we have and of the software and of the data that is stored on it. So that's why we are really transiting to hosting everything on GitHub repositories and keeping the documentation very clear and easy, so that when new students will want to reproduce the research, or when new IT administrators will have to manage the infrastructure, all of this will be as easy as possible. We need to also keep publishing the software and the pipelines on the Escape software catalog and on the VRE. Future plans include using the Gambit software to combine different results, and the connection with HPCs, commercial clouds, and other external computing resources has been explored, for example, by the Euro HPC project. And also the caching of data and distributed storage on the VRE is still being explored through collaborations with the Lucio and Ariana projects. So as you can see, it has been a very nice project to work on, and there is still a lot to do and a lot to keep going, and we're looking forward to keep working together. And with this, I think we thank all of the members of the Dark Matter project, and we leave a bit of time for questions. And we leave our emails in case you have questions for later. Thank you.
Thanks, Elena. Thanks, Jared. I think it's a perfect summary talk to wrap up all the work they made in the last few years by the whole team. So I leave the floor to others for questions, if there are any, or comments. I also see that Ian and Javier are connected. They want to provide any additional comment to this webinar.
Well, since you put me on the spot, I think it was a very nice talk, and I will be certainly referring to this in several upcoming talks that I have to give in the next few weeks. I think one thing is the VRE is a really nice integration of the tools from EOSC Future and also from Escape, and as I think Elena said, probably makes it a lot easier to understand how to put all this stuff together, because it is quite complex. So I think that's a really nice result, and that's certainly something that we should make sure that we capture for the future. So thanks to you.
Yeah. Thanks, Ian. Thanks, everyone, especially Jared and Elena, for putting this together. The webinar will has been recorded, will be put on YouTube, and I think it will be a reference for future work. So with that, I thank again everyone for attending, and we'll meet perhaps somewhere in the future. Bye.
Bye.
Bye. Bye. Bye. Thank you.